So, hi, I'm Daphna from DSI, and in this talk, I'd like to share with you my adventures while participating in a challenge that took place in the summer of 2020. Now, the challenge was hosted by the Israeli Ministry of Defense R&D department with the goal of differentiating between humans and animals in signals acquired from radar systems. It introduced a fascinating real-world problem with real data and a lucrative prize pool attracting quite a lot of attention. Now, throughout this presentation, I will attempt to answer these three questions. Is it even possible to distinguish a human from an animal in radar signals? Do we need domain expertise, or is it a transferable problem? And third, can we exploit unique features of the data to generalize a solution from extremely scarce and imbalanced data? So, to answer the second question, a little bit about myself. I come from the world of computer vision and machine learning, and my experience with signals processing is mostly during my days at the Technion many years ago. So, my skill set around radars while entering this competition was, let's say, limited. But let me share what I have learned during this challenge. So, the basic concept of the radar system is pulses of radio signals that hit a target, which in return reflects the signals back to the antenna. The system makes use of the Doppler effect, which is a frequency shift of the signals a frequency shift of the return signals caused by the object moving either towards or from the radar's antenna, thus enabling to extract frequency levels or velocities of a moving target. Such occurrences are commonly represented using a spectrogram, which is a visual representation of the spectrum of frequencies returned over time. Here is a real example of a moving target. The y-axis represents the frequency levels or velocities, and the intensity in each level is defined by the heat map. Now, the frequencies are represented in a cyclic manner, where low frequencies are at the edges of the spectrogram and maximum speed is at the center. In this example, there's an obvious target moving towards us. But there's also noise caused by signal disturbances and what is called clutter, which are signals received from the background environment, such as swaying grass and leaves, focusing mainly around the edges, low-frequency edges of the spectrogram image. If we make an analogy to computer vision, this spectrogram can be compared to, say, a short clip of a dog running towards us. But what in the nature of the target signals can differentiate a human from an animal? So for this, the micro-Doppler effect come in, which are the small frequency shifts caused by the motion of the target within itself. Those micro-Doppler signals around the center of mass actually represent the movement of the limbs, like the arm or the foot, or perhaps the tail. So actually, the nature of these signals is what can help us differentiate between what is human and what is an animal. But easier said than done. In real spectrograms, with the target patterns merging with the noise and clutter, it's impossible to distinguish between the two, at least for the untrained eye. But how about a deep neural network? Okay, but first, some statistics about the provided data. So, the training data consisted of short segments extracted from occurrences of targets from 7 different radars at 7 different locations and terrains, like desert, mountains, forests, etc. Now, if we again make an analogy to vision, these can be compared to, say, 7 static cameras looking at varying locations and terrains. And while the first 2 consisted of a balanced number of human and animal segments, the other 5 had either only animals or only human occurrences. In addition, There were way more samples from the one-class radars, as opposed to only a few samples from the balanced radars, resulting in a very unbalanced representation. And if we, yes. In addition, there were very long samples, many samples from long occurrences of the same target, and also a few short samples, collected from very short occurrences. So the test set, on the other hand, included new locations unfamiliar to the training set at training time and had a balanced distribution of human and animal samples and occurrences. So, if we once more make an analogy to computer vision, with the classic cat and dog image classification task, this may be comparable to having a few images of several dogs playing outdoors and images of a cat at the same location, and many such images of that same cat. So, test image of, say, a cat at the park or a dog on the couch may very well confuse the classifier. So, in short, samples from same occurrences will have very similar features, challenging good generalization. And classes limited to specific locations will challenge new predictions on new locations. Now, thankfully, we'll see later why, the organizers also supplied us with very useful auxiliary data, which included signals acquired through background-only segments. So it was obvious a solution would have to tackle these challenges, to balance the data, to avoid learning features of the background rather than of the target itself, and to manage to extrapolate well from the training data onto the test data. Now, in the following slides, I will focus on three main components of the overall solution. So first, and to monitor the training and without overfitting, a careful selection of a reliable training validation split was required. So the samples from two locations, one of humans only and one of animals only, were withheld entirely from the training set, along with a short set of samples from the balance sensors, completing the validation split. This enabled to first evaluate performance on new locations and still ensuring that the same background does not result in the same prediction. So standard random splits or cross-validation schemes were useless in this case. Were useless in this case. And with some trial and error, this split was set constant throughout the development. To further tackle the problem of imbalanced data, data balancing was performed during training. So first, in each epoch, up to 3 random samples were chosen per occurrence, so that long and short occurrences will have equal representation per epoch. And each mini-batch consisted of an equal number of animal and human samples, so that equal penalty will be given in the loss function to human and animal mispredictions. These batches of spectrogram images were fed into a deep neural network for training, or more specifically, to a convolutional neural network for visual classification. Now, a key addition in provided a real boost in accuracy were the augmentations, to manage to generalize as good as possible from the challenging training data. Unique data augmentations were performed, fitting to the unique nature of the spectrograms. So first, if you recall my mentioning very useful auxiliary data of background-only segments, such backgrounds were randomly blended in various intensities into the training samples containing targets. So this, in comparison, can be viewed as creating new synthetic backgrounds to train from. This enabled us high robustness to noise and clutter. Also, random cyclic vertical translations were performed. So this is comparable to having the same clip played in slow motion, fast-forwarded, or even played backwards. You see, as long as the micro-Doppler signals, with the relations between those micro-Doppler signals remain intact, these translations do not affect accuracy or predictions, but rather help the model to generalize by focusing the network on what's important. So with the limit of 2 submissions per day, and this is me working on a submission while on vacation, we were honored with achieving first place and taking the first prize. Now, to conclude, and with cycling back to the beginning of our talk, this project offered a rare glimpse into the world of radar systems and their challenges, and proved that, at least in this case, these challenges can be tackled without vast domain expertise. It's interesting to see how, if you understand how to visualize, analyze, and manipulate the data well enough, a tricky data set can be exploited, and a seemingly uninterpretable representation can be deciphered using classic CNN models. So who's ever interested in further details and components of the solution, I encourage you to read the blog post or the competition website. And thank you very much.